Welcome to the Explainer. Today, we're cracking the code on a really cool algorithm. It's one that can find the absolute cheapest route, even when some of the roads actually pay you to take them.
So think about this for a second. Imagine you're planning a trip. You've got a map with all these different roads, and some of them have tolls. But here's the twist. Some of them offer cashback. They literally pay you to drive on them. So how in the world do you find the cheapest possible path when getting paid is part of the equation?
Well, this kind of problem is a real headache for a lot of the standard pathfinding algorithms you might have heard of. The famous Dijkstra's algorithm, for example, just completely breaks down. It gets its wires crossed by these negative weights. That's just the techie term for our cashback roads. But this is exactly the kind of weird puzzle the Bellman-Ford algorithm was built to solve.
So, how does it pull it off? What's the magic trick? Well, the secret isn't some big complicated maneuver. It actually comes down to a really simple but powerful process that it just repeats over and over. It's called relaxation. And honestly, that's the core clue to understanding this whole thing.
Okay, let's unpack that. Relaxation might sound a little abstract, but I promise it's super straightforward. It's really just about asking one simple question again and again for every single road on the map. Hey, is it cheaper to get to my destination if I take this specific road from where I am right now?
And here's exactly how it works, step by step. For any road going from, let's say, point U to point V, you just do some basic math. You take the best cost you know of to get to U, add the cost of the road to V, and then you check, is that total better than the current best price for V? If the answer is yes, if you've found a better deal, you just update your map with the new, cheaper price. Simple as that.
Now here is where the real genius of the algorithm starts to shine. It doesn't just check each road once and call it a day. Oh no, it does it systematically, again and again, kind of like a super patient detective who investigates every single lead until the full story finally comes into focus.
So that brings up a huge question, right? If you just keep checking and checking, when do you actually stop? How many times do you have to comb over the entire map before you can confidently say, okay, that's it, we found the best possible path to everywhere? And the answer is surprisingly elegant. Think about it. If you have, say, V number of cities on your map, what's the longest possible path you can take without ever hitting the same city twice? It's always going to be V-1 roads. Any more than that, and you'd have to be making a loop. So that's what the algorithm does. It methodically checks every single road V-1 times, guaranteeing it finds even the most roundabout longest possible simple path.
All right, let's actually see this in action. We'll start our investigation at the source. The cost to get there is, 0. As for everywhere else on the map, we have no idea how to get there yet, so for now, we'll just say their cost is infinity. Then we start pass 1. We relax every single road. This instantly tells us the cheapest way to get to all the neighbors directly connected to our starting point.
And you can see the result right here. The cost information is starting to spread out from the source, kind of like ripples in a pond. After just one pass, we've updated our map. We now know the cheapest way to get to location A is 7 and to B is 6. But notice C, it's still infinity. Why? Because you can't get there in just one hop from the start.
Okay, so now we're ready for pass 2, and this is where it gets interesting. The key is we now know the cost to get to A and B, so we can use them as new launch pads, potentially unlocking even cheaper routes to places further down the line. Let's see what happens.
And whoa, look at that! The distances just keep getting better. The cost to reach A actually dropped from 7 down to 4 because we found a clever shortcut through another location. And we finally found a path to C. This whole process just continues, with the costs only ever going down as the algorithm relentlessly sniffs out these longer but ultimately cheaper routes.
But Bellman-Ford has one more incredible, absolutely critical trick up its sleeve. It's not just about finding the cheapest path, it's also about what it does when it encounters the most dangerous scenario possible, the infinite cashback loop.
So we've done all our required passes. The answer should be totally locked in. We should have found the cheapest path. But what if we decided to run the whole thing just one more time? What could possibly happen?
Well, if after all that work, after we've already done the maximum number of checks needed for any normal path, we run it again and find that a price can still get even lower, that's like a massive alarm bell going off. It tells us something is fundamentally broken with our map.
And that is the smoking gun. It means we've detected a negative weight cycle.
It's a loop of roads that actually pays you to go around it. You could just circle it forever and ever, driving the cost down to negative infinity. At that point, the whole idea of a cheapest path is completely meaningless.
And this is a really important point to get. The algorithm is smart. It doesn't get stuck in that infinite loop trying to solve an impossible problem. It wisely stops, raises a flag, and basically says, hey, this map is broken. There's an infinite money cheat code here, so I'm stopping. This is also why you can't use it on a simple two-way road that pays you. Going back and forth would be an instant infinite exploit.
So, with all that in mind, where does Bellman-Ford actually fit into the world of pathfinding algorithms? It's time to bring in the verdict.
This table really lays out the core trade-off. On one hand, you have Dijkstra's algorithm. It's fast, for sure, but it hits a brick wall with negative weights. Then you have Bellman-Ford. It's definitely slower, but its special ability to handle those cashback roads makes it way more versatile and powerful for a whole set of problems that Dijkstra can't even begin to solve.
And this chart just drives that point home visually. You can see Bellman-Ford is just a more work-intensive process. Its runtime, V times E, depends on the number of cities times the number of roads. That's a lot of work. But that extra work is the price you pay for its superpower, handling those cashback roads and detecting those dangerous infinite loops. So let's boil this all down. If you remember anything from this, remember these 4 things. 1. Bellman-Ford is your go-to for solving the cashback problem with negative weights. 2. It's a brilliant detective, cleverly sniffing out those impossible infinite loops. 3. It does all this by being a workhorse, relaxing every single edge over and over. And 4. Always remember the trade-off. It's the slow and steady tortoise to Dijkstra's hare, but that's what makes it so powerful and safe. And that kind of leaves us with one final thought. This is really about more than just finding paths on a map. At its heart, it's a method for finding hidden, exploitable loops in any system. Which really makes you wonder, doesn't it? What kind of hidden loops could an algorithm like this find if we pointed it at our own complex systems, like financial markets, social networks, or even global supply chains?